Hi folks, today we're going to be learning about functions and a bunch of vocabulary words that have to do with functions, because functions are going to be really important for things we do all year with Algebra 1 and in future years as well. So before I give you a definition for function, first let me give you a definition for relation. A relation is just any pairing of inputs with outputs. You put something into an equation and you get something out of an equation. A function is a relation that pairs each input with exactly one output. So you can't have one input giving two or more different outputs. And that's what we're going to look at here, what makes a function different to a relation. So there are a bunch of different ways to represent relations and functions. You can use input-output tables, like these shown here, mapping diagrams, like C and D here, lists of ordered pairs, like E and F here, or graphs. And all of these are ways to show relations and functions, but we're going to look at these and we're going to figure out, hey, how can I tell if that relation is a function or not? So let's look here at these input-output tables, and you can see that for each x value, I have a y value. For each x value, I have a y value. And if you look at these x values here, there are no repeats. There are no repeats. Therefore, we can't possibly have any x value with two different y values. Therefore, this is a function. If you look at relation B here, I have -2, -1, 0, 0, and 1 as my inputs. Notice here there's a repeat of my x values. There's a repeat of my x values with different y values. Because one x value can produce two different y values, this is not a function. So this is how you use the definition of function to identify a function. Let's scroll back up here. A relation that pairs each input with exactly one output. We need to look at the inputs and make sure that no inputs are repeated, and if they are, that they only go to one value, not more than one. Let's look at a mapping diagram. Here we have different inputs and we have different outputs. Notice that there is a case where I have two different inputs going to the same output. This is okay in a function. You can have two different inputs going to the same output. You just cannot have two different outputs for the same input. So this is a function. We don't have any repeated x values that are going to different y values. On the other hand, this mapping diagram here has the input of 1/2, and the input of 1/2 could have many different results. It could go to -2, to 0, and to 4. And therefore, this example D here is not a function, because one input could result in multiple different outputs. So the basic rule here is that we don't have a function if any x value is ever listed with more than one y value. Input and output tables and mapping diagrams are fairly easy to read, but lists of ordered pairs take a little more work. So if I look here at -2, -1, 0, 1, and 2, those are my x values. Those are my inputs. Let me use a different color here. My outputs are 2, 2, 2, 0, 0. So if you look at this example, the outputs are repeated. We've got 2 a few times, we've got 0 a few times, but this is okay. This is similar to this example here where you have repeated outputs. The important thing is that there are no repeated inputs. So this example is a function. If we look here at our inputs, we've got 4, 8, 6, 4, and 5 as our inputs. And if you notice, there is a repeat here. We repeat those 4 values, and therefore, and when we repeat those 4 values, we have different y values, 0 and 3. Okay. If we had seen the example of 4 with 0, that would not have been a conflict with this data point because they would have had the same input and the same output. You can have repeated x values so long as the y value is the same. You cannot change the y value. You cannot ever have one x value listed with more than one y value. This second list of ordered pairs here is not a function. Let's look at graphs. Graphs require a different approach, although in some ways it's easier. The way you can use a graph to determine whether the function is the relation is a function is to use what's called the vertical line test. And you can see there's a dotted red vertical line here on graph G and a dotted vertical line here on graph H. Basically, your vertical line, if the relation is a function, should never pass through the graph more than once. And no matter where I slide this vertical line on this example, the vertical line never passes through the graph more than once. So G is a function. On the other hand, if I look at H here, my vertical line passes through the graph here and here. Passes through the graph more than once, therefore this graph H is not a function. It's important to realize that even one line passing through 2 points is enough to make the relation not a function. It doesn't have to be all over the graph. The vertical line passes through the graph more than once. It could just once is enough to make the relation not a function. Relation I here, no matter where I place my vertical line, it only passes through the graph once. So this is a function. Here, sometimes when I draw a vertical line, it only goes through one line. But remember, once is enough to make it not a function. And right here, my vertical line passes through 2 points. And right here, my vertical line passes through 2 points. So this one is not a function. So the vertical line test is a faster check for whether a relation is a function if you have a graph, as opposed to one of these other relationships here. What other information do we need to know about a graph? We need to know about domain and range. So I'm going to scroll back up here to our some definitions that we have. The domain is the set of all possible input values. When I talk about input values, I'm talking about that x value. Range is the set of all possible output values, all possible y values. And this vocabulary just lets us differentiate between the x values and the y values, the domain and the range. So sometimes, depending on the layout, sometimes determining the domain and range is really easy. Here on this, in an input-output table, the domain is all listed in one column, and the range is listed all in another column over here, range. Looking down here, the domain is listed in one row, and the range is listed in another row. Similarly with a mapping diagram, the domain is listed in one bubble, and the range is listed in another bubble. The domain is listed in one bubble, and the range is listed in another bubble. Down here with our list of ordered pairs, I've already kind of highlighted in relationship E, all of my domains are listed or have a red arrow pointing to them. And all of my ranges have a blue arrow pointing to them, the x values and the y values. So you could list them out in a list. My domain is includes -2, -1, 0, 1, and 2. And my range includes 2. I don't have to list 2 more than once. Range is 2 and 0. For this other list of ordered pairs. I did not highlight my range, so let me go ahead and do that now. And then here we see the domain would be 4, 8, 6, and 5. I don't have to list the 4 again. It is considered polite to kind of list things in order, so that would be 4, 5, 6, and 8. And then my range would be 0, 7, 4, 3, 2. So that's 0, 2, 3, 4, 7 in that order. Looking at graphs, we can't give the domain and range of graph G here or H because they aren't labeled with numbers, so we don't know the exact numbers. But I can look at graphs I and J and give domains for those as well as ranges. So here, my graph kind of goes from -2 or -3 all the way up to +4, but I have arrows on either end of my line, which indicate that the line goes on forever. So really my domain here is all real numbers because my line extends for forever in every, in both the -x and the +x direction. And then my range, similarly, will also be all real numbers because my line extends up and down in forever in the +y and the -y direction. So remember, the range has to do with y values, which are up and down, and the domain has to do with x values, which are left and right. With example J here, we have our domain. Let's see, I have points at 1, at 2, at 4, and at 5. And my range has values at 0, at 1, at 2, and at 5. So when you have discrete points like this, you can list the points you see from the graph individually. Let's look at how to figure out the domain and range of 2 other types of graph that you may come across. So with these graphs, notice these are not individual points that we're trying to identify, but it's also not a continuous line that extends forever in either direction. So how do we express the domain and range of these types of graphs? Well, we learned about open circles versus closed circles in our chapter on inequalities. And we learned that open circles means the line kind of comes right up to that point but doesn't include that point. And with a closed circle, the line goes up to that point and does include that point. So what we have here as we read this graph, and the domain is all about the x direction, I go from -2 up to +3. So my x values can be anywhere between -2 and +3. And x has to be greater than -2, not greater than or equal to, because that's an open circle. And the domain has to be less than 3. Again, not less than or equal, because this is an open circle. Similarly, for the range, which we can do in the y direction, we go from -1 here up to +2. So for my y values can go from -1 up to +2. And again, I'm using less than symbols, not less than or equal to. For the graph that I have over here, my x values, and it's this exact same graph with the exact same numbers, it's just that my circles are closed in. So here my domain would be -2 is less than or equal to x is less than or equal to 3. And here I'm using less than or equal to symbols because those are closed circles. Similarly, for my range numbers are the same. The dots are in the same position, but I go from -1 to +2 with equals signs also included there in my inequalities because those points are colored in. Those points are included in the solution. So this is how you can use different ways you can identify the domain and range of different relations that might be presented to you in different formats. So let's look at a real world example here of domain and range and whether something is a function. So water pressure is 0 psi at sea level and increases by 0.44 psi for every foot an object descends in water. So psi is pounds per square inch, and so we're looking at how to kind of, in order to answer the question, is this a function, we need to kind of know what our equation is, what the relationship is between water pressure and how many feet we are below sea level. So if we just kind of decide that the number of feet we are below sea level is F, and then our water pressure is P, then we can kind of come up with a relationship between P and F. And pressure starts at 0 psi and then increases by 0.44 psi for every foot an object descends in water. So basically, I want some sort of rate times the number of feet that I have. And because of this value here, that's my 0.44 that I multiply times my number of feet. It's my rate for every foot that I descend. Of course, I don't actually need to include this 0 plus here. Sometimes you have an initial starting value and other times you don't, and in this situation we don't. So I can kind of rewrite this without the 0 there, because 0 plus any number is just itself. And here is my relation between F and P. And is this a function? Remember, our definition of function is any input we give it, there is only one output. And in this example, our input is F, the number of feet we are below sea level, and our output is the pressure. And anytime I put a number in here for F, there's no alternate choice for pressure. There's only one possible pressure. There isn't somehow we could do the calculation differently, 0.44 times F, and get a different value. So this is a function because there's only one P for any F value we plug into the equation. So now the next thing we're being asked is, what's the independent variable? What's the dependent variable? Well, the independent variable is kind of, if you think about a cause and effect relationship, this is the cause, and then the dependent variable is the effect. Another way to think about it is that the independent variable is the thing that the researcher or the scientist or the investigator decides to change. And I remember this because I'm an independent woman and I can choose what I want to choose, and I choose the independent variable. The dependent variable, on the other hand, depends on the independent variable. It's dependent on something else. I don't get to choose it. It depends on the other variable. So, and if we look at these kind of definitions we have up here, the independent variable is the variable that represents the input values. It represents the domain. So that's another way to think about it, is the input values or the domain, whereas the dependent variable represents the output values or the range. So coming back down here to this question, the independent variable, I'm talking about the cause, or I'm talking about the x values or the input values. And here we have the input values. The cause is the feet we are below sea level. The feet determine what the pressure is, not the other way around. It's not that the pressure somehow determines how many feet we are below water. So the cause is the feet. F stands for feet below sea level. Sea level. And then the dependent variable depends on that independent variable. And in this example, this would be our P, our water pressure. When I ask about domain and range, remember domain has to do with the independent variable and range has to do with the dependent variable. So I'll still kind of color code this. The domain, the set of inputs I can use. I want to know what range of values I can use for f. And this problem tells me that they want me to give the domain for a whale that can dive from anywhere between 1,000 feet below sea level and 3,500 feet below sea level. And so my f value can be, since the whale starts at 1,000, it can be equal to 1,000. And because it ends at 3,500 feet, the f can be equal to 3,500 feet, but otherwise f needs to lie between those two values. Of course, if we plug in that range of values, we will get pressure values. And on the low end, pressure can be, we can use our equation, 0.44 times the feet below sea level. So on this side, I've got 1,000 times 0.44, and that's going to give me, oops, one too many zeros there, 440. And then on the high end, I'm going to have 3,500 times the 0.44 again. And on the high end, the highest value would be 1,540. And this is all PSI. These ones were all feet. So I have a domain between 1,000 and 3,500 feet, and I have a range of 440 to 1,540 PSI. Let's look at another real-world example, this time a geometry example looking at the perimeter of a square. Now the perimeter of a square, the perimeter is kind of like how much fencing you would need to box in this area. And of course, in a square, each side has the same length, so we're going to call that length S. And to get the perimeter, you just add up all four sides. So basically it's 4 times the value of s. So we get this equation here, p equals 4s. So first we need to determine, is this a function? Yes, it is, because no matter what value of s we put in, there's no way to kind of branch off and get a different answer. We're always just going to get one possible answer for p. So yes, this is a function. Next, let's look at the independent variable, the thing we get to choose, and then the dependent variable, the thing that it depends on the independent variable. Well, we have two variables in this equation, p and s, and one of them is depending on the other. The thing we kind of can control more, the thing we get to choose, is the length of one side of a square. We can choose how big the square is, but then the effect is the perimeter changes as a result of that. As we increase the length of a side, the perimeter also gets bigger. So here the independent variable is s, which was the length of one side. And here the dependent variable is the perimeter. Now that we know which is the independent variable, which is the dependent variable, that's going to help us answer our next question, which is asking about domain and is asking about range. And domain is always related to the independent variable, and range is always related to the dependent variable. So what are our possible domains in this problem? Well, the length of a side of a square, it has to be positive. You can't have a negative length to a square, but it really could be any value. It could be whole numbers like 1, 2, 3, but it could be values in between like 1.7 or 2.4. So really, so long as our S value is greater than 0, then that is a plausible input value. Remember, we're looking for inputs here, a plausible input value to this problem. Doesn't make sense to have a negative number, so it doesn't make sense to have a square with a side length of 0, but so long as it's a positive number, you can have a square of any size. It could be really small or it could be really large. Our ranges, similarly, our ranges, the set of possible perimeters, our output values, also have to be positive numbers. The perimeters cannot be 0. The perimeters cannot be less than 0. They have to be bigger than 0. It's true that the perimeters have to be bigger than the side length, but no matter how small you make your perimeter, you can always find a smaller number for the side length, and so it is sufficient to just say greater than 0. Let's look at another geometry example that's just a little bit different here. This time we're doing the sum of the interior angles of a polygon with n sides. We can calculate that sum of the interior angles by using this equation, S equals the quantity n minus 2 times 180. And so in this example, let's look at an example quickly here. If I just draw a triangle, this equation tells me that the sum of interior angles of a triangle should equal 180 degrees. Why is that? Because a triangle has 3 sides, and if I take that number, 3 sides, and subtract 2, and then multiply times 180, that gives me 1 times 180, which is just 180. So I can figure out what the interior angles add up to using this formula. So I'm being asked, is this a function? Well, yes, it is. No matter what value I choose for n, I will get a different, a unique value of s. There's no way that I can kind of take a different path and get a different answer for s. Every value of n produces a different value. It produces an s that is I can't possibly have 2 different values of s for the same n. So let's look at our independent variable here, what we get to choose, our kind of input value. Our independent variable is the number of sides on the polygon, this n value here. We get to decide how many sides our polygon has. On the other hand, the output value, the thing that depends on the number of sides, is that sum of interior angles. So once again, this is our output values, or this has to do with our range. And our input values have to do with our domain here. So what's our domain and what's our range here in this problem? Here, even though this is another geometry example, our situation's a little different than the previous example, because here our domain could be any value, even kind of decimal or fraction values greater than 0. That's not true here. The smallest polygon you can have has 3 sides. I can't draw a polygon with just 2 sides. I can't connect it back up again. So, and also, the number of sides has to be a whole number. I can have 3 sides, 4 sides, 5 sides, but I can't have 4.5 sides. So our domain here is going to be only whole numbers that are greater than or equal to 3. Whole numbers greater than or equal to 3. And so you could just express this as being 3, 4, 5, ... So just kind of continuing the pattern here for our range, for our domain. For our range, on the other hand, these are our output values. But we can't actually just have any old output value because we have very specific input values that we can put into the equation. No matter what we do, our output values are going to be multiples of 180. Our output values will be multiples of 180. Of course, the smallest multiple of 180 is right here, 180. And then we can go up from that and have 360, and we can go up from that and have 540. And so, and we can just kind of do dot, dot, dot to say that the pattern continues. But here we have really discrete domain and range values instead of just a whole kind of continuous set of domain and range values, the way we did for the previous example. I hope this helped.